Okay, this is the walkthrough video for the Quantitative Reactions lab. The term quantitative means that we're going to be carefully measuring the amounts of reactants we combine and the amounts of products we obtain, and we're going to calculate a percent yield for the reaction based on the stoichiometry. We're going to be looking at the reaction between sodium carbonate and calcium chloride. Pure sodium carbonate is a white solid, but as you can see, we have a 1.000 molar solution of sodium carbonate dissolved in water. The calcium chloride is present as a solid, calcium chloride dihydrate. This is a hydrated salt, which means that there is water in the solid structure. For every calcium chloride, there are 2 water molecules. This needs to be taken into account when calculating the molar mass of the solid. We're going to be dissolving the calcium chloride in water eventually. Once it's dissolved, we can ignore these waters of hydration, since they just become part of the water of the aqueous solution. In other words, take the 2 equivalents of water into account when finding the molar mass, and using that to convert mass to moles. Once you have the number of moles, no need to account for the waters of hydration anymore. Starting from our reactants, we're going to prepare 2 aqueous solutions. Since we'll need to know the molarity, we're going to prepare these in 100 milliliter volumetric flasks. A volumetric flask is used to very precisely measure exactly 1 volume, in our case 100 milliliters. If we zoom in, you can see a mark on the neck of the flask. When the liquid level sits exactly on this line, we'll know that we have 100.00 milliliters of solution in the flask. Let's prepare our solutions, starting with the calcium chloride. I measure out 1.845 grams of calcium chloride dihydrate on the balance. I then use a powder funnel to transfer the solid into the volumetric flask. All of these measurements will be included in the lab document. I rinse the weigh boat into the flask to make sure all of the solid is transferred. I proceed to add about half the water we'll need and shake the flask. All of the solid needs to be dissolved before we add the remaining water. Once all of the solid is dissolved, I add the rest of the water until the liquid level reaches the mark on the neck. I need to do this slowly and carefully for the last few milliliters because if you overshoot the volume marker, you have to start completely over. I cap and shake the flask to make sure everything is homogeneous. The water level fell very slightly after doing this, so I added a bit more water to bring it up back to the mark, followed by mixing it again. Now let's make the sodium carbonate solution. For this, we're going to need to dilute a more concentrated solution to a lower concentration. I use a graduated pipette to measure 10.00 milliliters of the 1.000 molar sodium carbonate solution and transfer it to an empty volumetric flask. I then add about 1/2 of the water and mix before carefully adding the remaining water to reach the 100 milliliter line on the flask. I cap and mix the flask again before topping it off. Now we can combine our solutions to perform the reaction. I transfer the calcium chloride solution to a 250 milliliter Erlenmeyer flask. I now add the sodium carbonate solution to the same flask. Immediately, the combination of these 2 clear liquids produces an opaque white suspension. An insoluble solid has formed. I swirl the reaction mixture to make sure both solutions mix together and completely react. Before filtering off the solid, I record the mass of a watch glass and filter paper. We're going to collect our product on this filter paper, so we need to know its mass before filtering. Now we'll filter the reaction mixture. I assemble the filtration apparatus and take the same filter paper from before and place it in the filtering funnel. I add some water to get the paper to stick to the bottom of the funnel. I turn on the vacuum and pour the reaction mixture through the apparatus. The filter paper will catch the solids, but the vacuum will draw all the liquid into the vacuum flask, including any reaction products or unreacted reactants that are still dissolved. Once the liquid is all drawn through, I turn off the vacuum and remove the funnel. You can see the white solid collected on the filter paper. After removing the filter paper with the adhering solid, I transfer it to a watch glass. If we weigh our product right now, there will still be residual water that will artificially inflate the mass. To address this problem, the product is placed in a lab oven set just above the boiling point of water. After about 10 to 15 minutes, the product is removed from the oven and weighed. The product is returned to the oven to dry for about 10 more minutes. We will know all of the water has evaporated once the mass of the product stops decreasing between oven cycles. After 10 minutes, the product is removed again. After weighing, the mass has not appreciably changed from the previous reading. This indicates that the water is all evaporated, and we're only weighing the solid that was collected with no residual water. All the data you'll need to complete this experiment can be found in the lab document. It will be up to you to use that information to calculate percent yield and all the steps you'll need to calculate to lead up to that. Okay, that's all for quantitative reactions. Please contact your instructor with any questions you have after watching this video and reading through the lab.